secure edge AI, why we need it. Although latency is often the main reason for edge computing, there are many benefits to placing workloads as close to where the data is being created and where the actions are being taken. So definitely latency is number one. And then data volume and bandwidth considerations, including wide area networking cost. The amount of data being generated at the edge is exploding, with the estimates describing 70% of enterprise data being generated outside of the core by 2025. So the core here is defined as the hyperscale cloud, and enterprise-owned data centers and enterprise data centers. And the third reason is security, privacy, data sovereignty, and compliance. And the fourth reason for edge computing is the need for autonomous or disconnected operations. In other words, less reliance on good quality connectivity to a centralized cloud. And this is particularly true in industries like oil and gas, with the remote operations, with the not so much reliable connectivity. Edge computing does not compete with cloud computing. So the cloud computing continues to grow, but edge computing does not compete with it, but actually complement and complete it. Complement and complete. So edge computing augments and expands the possibilities of today's primarily centralized hyperscale cloud model and enables deployment of the IoT and entirely new digital business applications at the edge. We define on-prem edge with latency target of 5 milliseconds and network edge with latency target of 20 milliseconds. So these edge servers and gateways, either on-prem or at the network edge, serve a critical role of intermediary processing node and integrators between multiple cores. So not only one core, there can be another core between multiple cores, and a diverse set of people, devices, processes, and workloads at the edge. Now we know the top 4 reasons for edge computing. Let's look at some of the use cases of edge computing. Many of the edge AI users are around the convergence of the physical and the cyber. As we know, the digital business relies on the convergence of the physical and the digital to create new business opportunities and new business moments. So enterprises are using the edge model to create value from data, observations, and insights at the edge. A typical edge deployment consists of sensors and IoT devices connected to an edge platform, and this is deployed in, for example, factories, plants, retail stores, for example, healthcare facilities, and so on. So one common theme you notice here is these are places where the data is being created and where the actions are being taken. So you will find edge computing use cases at these places. And edge computing, for example, in the manufacturing sector addresses many Industry 4.0 initiatives. Industry 4.0, providing a high performance, low latency edge servers that can address industrial control and automation use cases. So a lot of the industrial use cases are around industrial control and automation, and as well as powering computer vision for video surveillance and safety, and drive innovative applications of augmented reality, AR and VR to improve productivity. So really Industry 4.0, closed loop automation, and AR, VR, closed loop automation. And let's look at some of these use cases. So we just learned that typical edge deployment consists of sensors and IoT devices connected to an edge platform. So the typical deployment will be like you have some sensors and some actuators. You want to take some actions connected to an edge platform. The sensor feed data into the edge, and edge delivers actions for the actuators, as well as you also get the observations and insights. So this is a typical model. And this you can see, this may be an edge device, like you can call it a device edge. It's basically over here, it's a device edge. Actually, you can do some of the quick and lightweight analytics in the device itself. Like you can have sensors, there can be some processing provider, sensors come in and actions delivered from the there. So device edge can do some quick and lightweight analytics as well with deployment of the analytics inference in the device itself. And let's look at an example of closed loop automation, and that is automated guided vehicles, or AGVs. Others examples can be industrial robots and so on. You'll see there can be, once we explain this AGV use case, you can see there may be many other these closed loop automation use cases. So AGVs are computer controlled and wheel-based carriers, so that travel along the floor of a facility without an onboard operator or driver. So there is no person driving this, no person. So they are in that way autonomous, and their movement is directed by a combination software and sensor-based guidance systems. And then the question is how an AGV, which is an example of closed loop automation, can benefit from edge computing. As we discussed over here, in theory, you can do device edge, like AGV can work as a device edge without an on-prem or a network edge. But the problem is the running the computer vision applications on the AGV itself can be cost prohibitive, and it can be power hungry. So the incentive to using edge computing is because running the computer vision applications on edge computing reduces the compute load on the AGV. This allows AGVs to be lighter, lower cost, and they can operate longer on a single battery charge. So, you see, like you can always do the device edge, but then you run into these complexity issues. And in some cases, when you are doing the on-prem edge or the network edge, you also get the benefit of aggregation, like because compute, there's a common pool of compute and analytics. You get analytics across multiple of these devices and so on. A second example of closed loop or latency sensitive application is augmented reality or extended reality. So extended reality that basically combines AR and VR. So, for example, AR-enabled connected workers can be one example. So AR can improve workers' productivity, enhance employee training, and make work sites safer. For example, AR overlays on real life, like augmented reality overlays of, for example, of the inner workings of industrial machinery, cars, airplanes, elevators, and other machines, allows for fast diagnosis of problems. So, for example, a broken part, snapped wire, overheating. So by using an AR headset, worker can access checklists and manual without interrupting their work. Now, you see like this AR overlays needs to happen in real time over the real world. So there will be sensors like with the AR headsets, the images of, for example, the machinery will be captured, then the analytics done at the edge computing platform, and then the overlay of information sent back to impose on the machinery, for example. So this, again, you can see you can do the device edge in this case as well, like put all the compute in the AR or VR goggles, for example. But then again, the battery life, the cost, the size of the device is going to, and the complexity is going to increase. And in warehouse operations, workers wearing the AR headsets can be directed safely and quickly to stock products. AR can help workers more efficiently load carts and docks and can also track inventory. So really using XR, AR, VR to enhance productivity for the industrial as well as warehouse and other similar applications. Yeah. A third example of AR applications is can be more for entertainments, like for events and venues such as sports, concerts, performances, and theme parks. And the goal there is of using AR is to deliver better user experience with like live information overlays, multi-camera, multi-angle views, and personalized instant displays. Yeah, so that's another latency sensitive application. A fourth example of latency sensitive application that can benefit from edge computing is multi-party cloud gaming. As we know, gamers expect a lag-free, data-rich experience. Actually, cloud gaming is an example of bandwidth-intensive and low latency application. And then you can have the edge computing and all the gamers connected through the edge computing, but it needs to, in a way, it needs to be either with an on-prem edge or a network edge. If some of the gamers are on the other side of the planet, then that's not going to help, like, because then the latency, just the propagation time is going to be prohibitive in that case. So as we pointed earlier, we see edge computing use cases at places where the data is being created and where the actions are being taken, like in and latency sensitive applications are where the actions needs to happen in with very low lag real time. Now let's look at a few use cases where latency is not the primary driver, but there is a need for local processing due to bandwidth concerns or security, privacy, compliance reasons, as well as for autonomous operations. So AI ML processing of video streams from 4K and 8K video cameras in the manufacturing process can be used for quality control. So this now the applications that are bandwidth intensive, but they are not delay sensitive. So you can use these for quality control, for safety concerns. And for example, with the video analysis, we can determine if workers are wearing compliance gear or not. Like, so you can determine that for safety concerns. And visual quality inspection, computer vision apps can ensure that the output from different manufacturing stages conforms to appropriate quality metrics. So the cameras can take pictures, and then the computer, with computer vision, you can find any faults. This automation of quality control allows for higher quality products with less human intervention. So at the same time, manufacturing safety records can be improved through the use of video feeds to spot potential safety violations and ensure that the precautions are taken. Like, so these are the use cases where now you have a large amount of data from 4K and from a large number of 4K, 8K video cameras that you need to process at the edge. And if it's not delay sensitive, you may say, okay, why can't I ship this data to the cloud? But then the problem is the bandwidth, like the WAN cost and other. If this is terabytes of data, we know the cost of shipping this data to the cloud can be very, very high. So the incentive there is the bandwidth conservation. And the next example we are going to see, just for compliance reasons, security, privacy, you may not like to ship this data to the cloud. And that next example is the bandwidth heavy application like medical imaging in healthcare. Like, so medical image generate large amount of data for analysis requiring local processing of sensitive patient data, like for security, privacy, and compliance reasons. Right? So you want to keep that data in locally, right? And you because there are compliance reasons, you cannot ship that data to the cloud and so on. So these are some example of the edge use cases. But one final point over here is what 5G has to do with edge computing. Right, so this is sometimes people relate 5G with the edge computing. So really, the question is what 5G has to do with edge computing. So as we discussed, most of this 70% of data, enterprise data that will be generated outside of the core will be generated by explosion of connected noisy and needy things. So there are going to be lot and lot of these connected, noisy, and needy things. Yeah. And 5G is expected to support IoT at scale. Like now, connecting a massive number of IoT devices using wires is not feasible, or it is cost prohibitive, right? What 5G does is 5G delivers reliable wireless connectivity with low latency for a massive number of IoT devices, right? So, and you can create like a 5G access. So again, from the coming back to the bandwidth question, you can create a lot of bandwidth like locally at the, for example, on-prem edge, and you can also deploy data centers fairly easily. But the real limitation generally is the connectivity between the edge and the core. So this is where the costs and latency comes into the play. And 5G just like we said, the edge computing doesn't compete with the hyperscale cloud or cloud computing, and similarly, the edge device edge also doesn't compete with the edge computing. It complements it because you can do some of the lightweight analytics at the device itself. Like, so 5G does not compete with Wi-Fi and wired Ethernet. So there will be still, you will have the Wi-Fi and Ethernet. And 5G is going to augment and complement it. Right? So because 5G is going to augment and complement it to support IoT at scale. I can say IoT at scale. Because 5G protocols are designed to support IoT at scale, like a massive number of IoT devices with the reliable connectivity. Actually, enterprises are seeking to centralize the visibility, management, analytics, policy enforcement, and other related functions across Wi-Fi, Ethernet, and 5G. And 5G is access agnostic. 5G can also support Ethernet and Wi-Fi with its edge computing and the authentication, authorization, and the networking protocols. Like, so you will see a 5G taking a central role where it's going to also support Wi-Fi and Ethernet access and enable this on-prem and network edge.